This is problem 10-9M. It's on page 589. The C-clamp in figure P10-9 is made of cast zinc ZA12. Determine the allowable clamping force that the clamp can exert if it is desired to have a design factor of 4 based on ultimate strength in either tension or compression. Okay, now they've given us a cross section here of the clamp, and it's just a standard C-clamp. Hopefully you've seen one before. Let's go and see if we can find material properties first of all. So we're looking for zinc, and by the way, I'm going to need some calculator help. I don't have this one right now. So
715.
715, thank you. Okay, 715, typical properties of stainless and non-ferrous. ZA12, yep, that works. So it's at the very bottom. So we've got an ultimate strength of 58 KSI. What are we in here? Oh, we're in metric units, so 400 megapascals. Yeah, so it's a factor of 4 based on ultimate strength. Now, they don't have any information in this table about a difference in ultimate strength in compression or tension. So what I'm assuming is that the maximum stress, now I say maximum stress, I'm going to calculate it based on the ultimate strength. So is this a shear or a normal? What do you think? If I write, I could write either a normal or a shear and write that it's a design stress based on the ultimate strength over 4. Well, the ultimate strength is 400 megapascals divided by 4 makes a nice round 100 megapascals, right? That's why he gave us this material, and then divided by 4, so we can do the math in our heads. So, but which one is it? It's a normal, isn't it? Because the ultimate strength is not the ultimate strength in shear, it's just the ultimate strength in tension, usually. Okay. Apparently they've measured it in compression as well, it's the same, so they just didn't tell it to us. So there's our design stress, and it is a normal stress, it is not a shear stress. Okay? All right, so we want to know how much clamping force. Well, we better somehow relate the clamping force to the stress in the material, right? In fact, we need to figure out where the stress will be highest. Now the cross section for the upper part, for the sake of the video, in case a student is watching this and does not have their book with them, let me sketch a rough draft of the clamp. Here's the knob back here, if you will. The section they've apparently identified is this section AA. And for that section, they've given us a cross-section view that looks like this. Because you see, it turns out there's actually thickness here that I have not drawn, and there's a flange that runs around the inside of this thing. Okay, so here's that flange just in cross-section. So this is view AA. And there's a 3 millimeter width here. There's an 8 millimeter width at the bottom of the flange, a 3 millimeter height to the flange, and
no, it's 3 from the bottom.
oh, you're right, it's 3 from the bottom. I looked at that 14 and I thought, what?
Oh, you can write 11 there.
Yeah, that would be 11. I'll stay with the book. So 3 millimeters there, and then 14 overall. That's better. Okay, so that should be everything we need. Okay, so that's all that the problem has told us. Now, what do you think about this? What kind of stresses are going to be present in here and why?
Tensile and compression.
Tensile and compressive stresses. Do you think there will be any shear?
No.
Well, I haven't shown you the loads yet, right? So it's not really a fair question. How do the loads go? Well, the load is just basically like that, right? An equal and opposite, let's just call it a load P. We're asking the question, what is the clamp load P that we can apply without breaking this thing, as long as you want a factor of safety of 4 against the ultimate strength. Okay. So I agree with you. I don't see any loads here that are going to cause any shearing at this section. Okay. So I think that there is just going to be normal stresses. Now, what will the loads look like here? Well, what we have to do is take a free body diagram. Remember, our goal is always to find the reactions, so we will want reactions along this line. That's where we want the reaction. So let me draw a free body diagram on the right-hand side of the clamp. we've got essentially a load P here. Well, then we must have a load P like that, equal and opposite, right? What else is going to happen?
Be a moment.
There must be a moment, because look, now we've got a force couple. So this height is really important. That's the moment arm of P. Which way will the moment have to act to prevent rotation? Clockwise or counterclockwise? Clockwise, you got it. The moment has to be like that. So we better calculate the magnitude of M in terms of P. In fact, M would be equal to what?
P times whatever the height is.
You got it, P times H, whatever that is. Okay? Now, they did give us some information. They told us that the distance from this point to this point, hold P over just a little bit. They told us that that distance was 26 millimeters. So what is H? It's a good question. 26 plus 7.
We have to analyze for the centroid first.
You have to analyze for the centroid, there you go. Because this height, what is this? This is essentially going to bend about something. What's it going to bend about? The neutral axis. So we need to know where the neutral axis is. Well, it's going to go through the centroid. Okay? So we've got to analyze it. Well, it's pretty straightforward. I would pull out the spreadsheet, but that would probably, let's see, would that be more? Yeah, that'd be okay. We'll pull out the spreadsheet. Why not? As long as the internet will respond. If it won't, then we'll calculate it by hand. I guess I better turn on the TV so that you guys can see what I'm looking at here. Windows has to think about if there's a new monitor in place. Oops. Wow. I've really upset the Windows gods now. I don't know what it's doing. I don't know why I didn't care that the other TV's turned it on.
We're the redheaded stepchild on this side.
The unpopular side. Okay, let's see. All right, so we first started looking at these things when we were talking about centroids. Let's go and grab the calculator spreadsheet. Just make the lives simple. Of course, we could draw this in SolidWorks if we really wanted to wait for SolidWorks to boot up.
Do you want to?
Probably not. Feel sorry for people watching this video. I never edit this part out. They have to just wait.
It's okay. There's a skip button on YouTube.
Well, you know what I usually do? I usually play videos about twice speed, because there's more videos uploaded in, what, an hour or a day or something that you can watch in your whole lifetime.
Yeah, I think it's something like a few hours per second.
Yeah, it's just ridiculous, yes.
I figured out I.
You figured out I? Okay.
It's 5.55.
I is 5.55, and that would be millimeters to the fourth.
Yeah.
Okay, good. Did you find the centroid?
Plus 26, so be 31.55 from the.
It can't be 31.55 because you only got 14 millimeters all over it.
I know, that's 5.55. That's where the centroid's at.
Oh, that's where the centroid's
Yeah.
at. Okay, let's see, does that make sense?
See.
That seems reasonable. So you're saying the centroid is at 5.55?
And it's AY over area total, right? Or summation of AY.
No, it's not just AY over A total. You have to locate the centroid of each of the areas
That's what it is.
and then weight them. So it's A times Y plus A times Y
Yeah.
divided by total area. Okay, all right. Did you say you got I as well, or no?
No.
That's okay.
You can do it.
We'll go through and do it here. Shouldn't take us too long. So we've got, let me take area 1 to be that lower area. So that is what? An area of 8 times 3 millimeters. Its location is going to be halfway up, so 1.5 millimeters from the bottom. And then the upper part will be, what, 14 minus 3 is 11? So 11 times 3 is 33. And its Y location will be at, let's see, 11 over 2 plus 3. Okay. The area moment of inertia for section 1 down here is going to be 8 times 3 to the third over 12. And for the upper area, that's going to be base 3 times height 11 cubed over 12, and we'll let the computer do the rest of the work. So good job, you got the Y location correct for the centroid. And then the area moment of inertia is 1031.59. Inches to the fourth.
I mean millimeters.
Yeah, millimeters, thanks. I'm bilingual. I speak both SI and English.
Okay. Metrical.
Metrical. All right, so why did we want that? Well, we need the height h. So now we know that the height h is 26 plus 5.55 millimeters. Okay, so that's going to be what, 31.55 millimeters? So that's where the neutral axis is located relative to the load P. Now, I've not drawn this very well because there is part of the clamp that extends on down here, but you know, we don't care about it because all we want is the distance from the load to the neutral axis. So let's write down H over here so we don't forget it. I'm going to need this space for the sake of the video. Let's see, and we'll write down the moment PH and just the load P as the loads that we have to concern ourselves with. Because now we're done with this, right? We've got the reactions, and by the way, let me jot down I too because I need a little more space. So now all we have to do is decide what sort of loads are going to be applied. Again, if the beam looks like this, you know, not drawing the right-hand side, I'm just drawing the cut face over here. Well, where do you think the stresses are going to be highest? Where's it going to matter most? Or just like on the left?
At the bottom.
What's that?
At the bottom, where it'll be in tension.
At the bottom where it'll be in tension. Well, that's a good idea, but notice when I erased this, I said, well, what direction is the load P? Well, it was like this. So yeah, you're right. Again, it's going to be at the bottom. For some reason, I was thinking that P was a compressive load. And so if that was the case, just like in the last problem, if P was a compressive load, then that would switch which side was critical, because you have compression from the moment and from the externally applied load P. But you're right, it is tensile. So where is the stress going to be greatest?
At the bottom.
At the bottom, right there. So that's the point we're actually interested in. Okay? Does that make sense to everybody? Just to make sure that you understand this, the moment is going to cause, let's see, which way was the moment?
It was clockwise.
Well, then wait a second, what we just said may be wrong.
Shouldn't the stress be the highest at the top?
The stress is the highest from the moment at the top and bottom. In fact, let me do this.
We make the top
Boy, let me show up on the video. Let's try this green marker. Oh, that's better. Yeah, you're right. It will be at the bottom. Because look, we've got tensile at the bottom, compressive at the top. And since the neutral axis is... Oh, wait a second. Wait a second. I'm not thinking right. It helps when I work these out ahead of time. The neutral axis is fairly down low, isn't it? Right? It's only 5 millimeters up from the bottom. And the stress is going to be proportional to the distance from the neutral axis. So the stress is actually going to be larger on the top. We'll have to check both the top and the bottom. Let me show you why. Because the distance to the neutral axis, or to the top from the neutral axis, is largest at the top and smaller at the bottom. Okay, so yeah, we have tensile stress at the bottom due to the moment and compressive at the top. And our other load P is tensile, but that doesn't necessarily mean that the stress will end up being the largest. Make sense? So we gotta be a little more careful than this. In fact, load P, let me change colors for P as well. We'll go with Christmas colors, even though it's not Thanksgiving yet. Oops. Okay, this load is going to cause a stress profile, something like this. And as we discovered in the last problem, a lot of times the direct stress due to this load is not going to be as important as the stress induced by the moment. So we have to be careful here. Anyway, let's calculate the stress from the direct load, P over A. We should have an area from the spreadsheet. Looks like it's 57 millimeters squared. I didn't write that down, but it's in the spreadsheet. So P is the externally applied load. Notice we don't know its magnitude, so we just have to write P over A. And the A, let's see. You know what, actually, let's do this. Let's stick with symbols, and let's just note that at the bottom, the stresses will add, and so the total will be equal to MC over I plus P over A, whereas, and actually, let's do it this way. Let's take a C1 and a C2 so we can distinguish between the two. We know their magnitudes, but I'm trying to do everything symbolically, because notice what we really have to do is solve for the load P that's allowable. And at the top, the stress, the total stress will be equal to MC2 over I, let's see, minus, and I could do it the other way, but I'd end up with a negative stress, it just meaning that it's compressive, right? So there's no need to do that. So minus P over A. Now, since the moment M is actually P times H, I can make that substitution, PH. Same thing up here. Okay. And now notice we know what the maximum stress can be, right? We know what our design stress is. So we can simply plug that in as the total stress and rearrange to solve for P in both cases. So in the first case, what would we end up with? Well, let's see. Let's do it step by step. Design stress is P multiplied by HC1 over I plus 1 over A. Right? And so solving for P, and let's see, well, we'll just have two different P's that'll work. We'll take it as the design stress divided by HC1 over I plus 1 over A. Okay. The upper one, I should still be on the video screen over here. Yeah, it looks like we've got some space. So I'll do this one a little bit more quickly. It's pretty easy to see what happens. It's going to look exactly like this, except we'll have a minus sign in it, obviously, right? So it will be P equals design stress divided by HC2 over I minus 1 over A. Okay. Now let's see, are there any unknowns in these equations? I don't think so. We've got geometry and stress. So we should be set, right? All right, so let's calculate, let's see, let's get rid of this because I need the space for the video's sake. So let's take care of P upper first. So 100 megapascals is our design stress. H, how do I do? Oh, fortunately I wrote it down. 31.55 millimeters multiplied by C2. What is C2? Well, that's the distance beyond the centroid, so that would be 5.55 from 14. So that's what, if I take 5 from it, 9, 8.45, is that right? So 8.45 divided by I, well, I we calculated in the spreadsheet, 1031.59 millimeters to the fourth minus, and I apologize, I'm going to have to get rid of this diagram, but we've gotten everything we need from it. So minus 1 over A, and A was, it was in the spreadsheet, it was 57 millimeters squared. Okay, so what units do we have here? Well, let's see, 1 over millimeters squared in both cases. And so megapascals, I'm trying to think if I put millimeters squared with megapascals, what do we get? I don't have that one memorized yet. I'll have to figure it out, times millimeters squared. If I add a 10 here, if I multiply by, not the 10, but 1,000, I multiply by 1 this way, then I could write gigapascals, right? And a gigapascal, I know, is a kilonewton per millimeter squared. And so, looks like I just get newtons out of this. Does that seem right? I think that's right. All right, so we'll just get newtons out of this. So plug it into your calculator, please. And of course, the other one is just the opposite of this. Of course, in this other one, we've got a different C dimension. We've got 5.55 there. And I'll write that out. P equals 100 megapascals divided by H, 1.55 millimeters, multiplied by 5.55 millimeters, divided by same I, 1031.59 millimeters to the fourth, minus, plus 1 over 57 millimeters squared of the area. Take care of this. Any numbers? Which one, top or bottom? Is what?
38.85.
38.85, thank you. Any second for that one?
I got 38.6, so.
38.6,
Yeah. I think mine was rounded.
rounded? Okay. How about the allowable load for the lower section? Yes, sir.
I got a question. Where did the 8.45 come from in the?
8.45 is this distance.
Okay.
We just calculated in our heads, we took 14 and took away 5 and 5.55. Good question.
Thanks.
You don't have a number for the lower load that's allowable? That number seems really small.
I was saying, I'm
wondering.
going like 415.
For this one?
Yeah.
I wondered if it was that or if it was that I made a mistake in my unit conversions. But you guys seem to agree, and that it makes sense. I mean, if a gigapascal is a kilonewton per millimeter squared, a megapascal should be a newton per millimeter squared. So I think that's okay.
It's also cast zinc too.
You're right, it is zinc. You're right, so it's not all that strong.
Right.
I guess I'm thinking of C-clamp that's forged, made out of steel.
Right.
And so my intuition is saying that's a really low load. So I guess we all know where this is gonna be sold, right? Every chance we have to throw them under the bus, why not?
Remember on the bottom, I got 58.55.
58.55?
Seems small too.
Well, here, we've got a powerful calculator over right here, let's just do it. So we got 100 multiplied by a quantity. It's not multiplied by, it's divided by, what am I thinking? And that quantity is 31.55 multiplied by, let's see, 8.45, we'll work on the top one first, divided by, well, I can just click in the spreadsheet, there we go, minus 1 over, and then I can just click in the spreadsheet to get the area. That should be it. So the top one is 415. And I'm going to cheat, since the equations are so similar, I'm going to copy the actual equation, paste it in the cell below, and just modify it, because the only thing that changes is the height, C, which is 5.55, and I have to add. So 533 is what I got for the lower one.
Well, could have been because you said it was gigapascals instead of megapascals.
I think that's okay, but we'll double check the units here in just a minute. 534 or so newtons. Yeah, I think that's okay. I think we still get newtons, but let's check the units just to make sure. We'll do it carefully. Megapascals multiplied by millimeters squared. Well, all we have to do is say a mega is a 10 to the 6th, right? And can we just say, I've seen you guys do this. Can we just say, let's see, millimeter squared over 1,000? Get rid of this, does that work? That doesn't work, does it? Doesn't work at all. Because there are 1,000 millimeters in a meter, but there's 1,000,000 square millimeters in a square meter. Does that make sense? Okay. So here's the way I like to do this. If I'm not sure, I do it this way. Multiplied by 1 meter per 1,000 millimeters. I know that's right. Right? No question about that. And then square the whole thing. That way the units get squared and the number gets squared. Now, you'll notice that the 10 to the 6 is going to cancel, right? Because this is going to be 1,000,000, because 1,000 squared is 1,000,000. The millimeter squared will go away, and we'll have pascals times meter squared. I know that a pascal is a newton per meter squared, so sure enough, we are getting newtons out of this. Okay? All right, so our result is in newtons, and I've erased it. It was 415.
Yep.
Which one's right?
That's,
I'm sorry?
that's a yes.
Yes. I'm like my brother-in-law.
Well, we're gonna be more concerned with the top one because that's the lower capability.
Exactly, right. This load will cause the top to break. This load will cause the bottom to break after the top is broken. Oh, wait a second, that won't work, will it? Okay. So which is going to break first, the top or the bottom? The top. Just like I said, our intuition initially didn't actually pay off, right? Because the moment, the stress profile due to the moment was not symmetrical, since the neutral axis was not in the center of the cross section. Well, it's in the centroid of the cross section, but it's not at the middle of the height. Okay. All right, any questions on this problem? All right.